Hello, welcome to my YouTube channel today. Today's video is a continuation from my last video. In my last video, I talked about my 8088 here on this breadboard that I'm building a bus controller for, or trying to design a bus controller for. And the last video emphasized or focused on the creating the ALE, the address enable latch, in maximum mode because it's not provided by the chip, it's provided by the bus controller. So today I want to talk about the ready signal. So the ALE is going to indicate the beginning of a bus cycle, and the ready signal is provided by the bus controller to tell the processor that the bus cycle is complete. And in between we can do what we want. So that's kind of, we've got the start and we've got the end. And we want to be able to make the distance in clock cycles between the start and variable based on what we want our bus controller to do. And as I stated in my last video, the bus controller that I'm trying to design is for the 8086 to work with a 16-bit ISA slot, which, if you're familiar with that, is also 8-bit compatible. And the 8086, this is 8088, but 8086 is not direct compatible with ISA. You have to have a bus controller in between. So it's set up a lot like before. I've got my reset, and I actually have a ready, like an external ready hold. 8284 clock here, and this is providing a clock signal at, this one's at 5 megahertz, and I'm using this for the bus controller. Down here I've got a crystal oscillator at 16 megahertz, and I'm using this to create an 8 megahertz signal for the V20 8088 here. If you remember my last video, or if you've seen it recently, I've abbreviated this so it's just the bare minimum of what I need to create the ALE. So we've got some counters here and an LS 138 and another LS 138 to indicate so the beginning of the bus cycle. So definitely check out my previous video to get an idea of how the ALE is working, and what I've done is abbreviated it here, and this would be the more finished product compared to the last video. So coming down here, I've got two more counters. These are LS 161s, and they've each got 4-bit output on them, and so they're going to count up and indicate what we're doing, what step we're on in the bus cycle. So we've got the clock in on the first counter, and we've got the rollover to the second counter here. And this would connect to essentially your 5 megahertz output on your clock here. This will actually, the intent is to run at a 4.77 megahertz to be compatible with the original PC, but I just stuck a 15 megahertz crystal in there today. So the outputs on your counters go over here to a ROM, and the ROM, based on what count you're in, you can decode through the outputs, the output 0 through 7 or D0 through D7, and you can use them as signal lines, so your I/O read-write, your memory read-write, etc. So over here, all I've installed is a bunch of counters, and these are just to slow down the clock cycle so that we can demonstrate that it's working, really. This whole row of chips, these 4 chips here, are just for nothing but slowing that, and these are just counters. So those would just come off in a later board. So right now the way I have it set up is the ROM has nothing but F's stored to memory, except for the last F, if you count up 0 through 7 on the outputs. This connects through address 0 through 7. So at address FF on the ROM, it's going to, the output for D7 is going to drop to 0. So it's going to be FE at that address. Everything else is FF. So this output is going to always be high until the counters count up to FF. Now, obviously, that's a lot of, that's 156 count. That's a lot of steps for a bus cycle, but it's just to demonstrate that these that there's a delay. The rest of the ROM is just connected to power and ground, and then all the other address lines are just typed low. So let me just demonstrate it working here. So as you've seen, let me reset it. It's F0 on the address, and there's a delay in between. And that delay is the count up on the ROM to the ready signal, and then once it's ready, it gives it the next count. And then, if you haven't seen my previous video, I'll explain that this is, by default, the data in on the processor is NOP 90, no opcode. So it just counts up, reading in NOP each time. So part of the bus control, and you know, this is more for my notes, so I can rewatch this and have my notes. Part of the bus control is there needs to be an external ready signal, and that's this button here will hold these counters here. So if you have an external not ready indication off the ISA bus, that's where it would go, is onto these counters. So let's just kind of show it more at full speed. So I'm going to take the clock line. See, it's not counting right now, so we're not counting up. I'm going to connect it directly to the clock. And this is why I've slowed it down. It's counting so fast, it's just going through all the addresses continuously. And you can see the ALE light is continuously latching. But, you know, you can tell it's actually working because the status 0 through 2 here is just showing a memory read or code fetch, which I would say it's not working if this thing was bouncing between different signals. So you definitely, if you made it this far in the video, you probably should check out the previous video to get an introduction to the board. But this just shows how the ready signal, let me put this back where how the ready signal would be implemented in a homemade bus controller. So the ROM is definitely the brains of the controller. The counter counts which step we're on in the ROM, and your output A through 7 are going to be different signals. To continue on, where we build on this is on your ISA bus. You've got a memory I/O chip select. Well, it's a chip select like 16-bit, and it indicates that it's a 16-bit card, and that would feed back into, say, one of the inputs on the ROM. And so the counters would be either counting up in a 16-bit read or an 8-bit read based on the external inputs. So by taking your statuses here, which would also be fed to the ROM, your statuses would be fed to the ROM, your address A0 and your bank high enable off the processor would be fed to the ROM's address lines, and then, as I said, the 16-bit chip select off the 16-bit ISA would all be fed into the inputs on the ROM, and that would basically think of like a high address select on the ROM, and then it would count up, counting at 0 based on the upper address select, and go through the steps of a read-write cycle, and it would either be an 8-bit to 16-bit to the processor, or such. So anyway, hopefully that wasn't too much rambling. Thanks for checking out my video today, and please subscribe if you haven't.